Good morning, and thanks for the opportunity to present my work on S=3/2 Kitaev spin liquids. This is the work that started when I was a postdoc at Imperial College London and continued up to now at Institute Laue Langevin in France. The results I will discuss here were published in this Nature communication that was recently released. But I will discuss as in this manuscript that's still in preparation now. So there are some new discussion. I don't think there's a need to a great review about Kitaev models since there were 2 talks this week about it. It's this model for frustrated model with exchange frustration on the Honeycomb lattice. And in the case of spin 1/2, we know how to solve. So a general characteristic of this model is the existence of an extensive number of conserved quantities, one for each plaquette. In practice, what theorists do to study this model is just to use this Majorana Fermi representation of the spins to map the spin model into a fermionic model. Now, these U operators here have this very special characteristic of commuting with the Hamiltonian and among themselves, so they can slice the Kitaev model into different sectors. You can by just replacing these U operators with numbers plus or minus 1. That's their eigenvalues. And it turns out that the Majorana representation of these WPs is just a product of these U operators around a plaquette. So that's why the WPs eigenvalues are often called Z2 gauge fluxes. Now, the ground state of the Kitaev model in the Honeycomb lattice turns out to be exactly known, the ground state sector, and it corresponds to the case in which WP equal +1 for all these plaquettes of the lattice. And once you do this, you can solve the model for any value of the exchange couplings here, J gamma. In particular, I draw attention to the isotropic case, for which the excitations of the Majorana fermions have this dispersion that's graphene-like. And of course, by varying the values of the exchange couplings, you can change from this gapless phase that I'm presenting here to some forms of gapped phases. Now, the relevance of the Kitaev materials to these heavy ion Mott insulators was already discussed by Eric on his talk. So what I want to draw attention is the new proposals for Kitaev materials with light ion Mott insulators. And the novelty here is that they allow you to implement the Kitaev model with different spins, including spin 1 and spin 3/2. And the spin 3/2 case have interesting, some peculiarities that make it interesting in its, the first one is experimental, because the candidates for Kitaev physics in S=3/2 were also the first materials that could be exfoliated down to monolayers, being the first magnetic analogs of graphene. You can see they present this ferromagnetic order out of plane. Now, when people try to make quantum chemistry computations of these materials to see what's the minimum model for them, they realize that the strong spin orbit coupling on the ligands, not on the magnetic species, induce Kitaev interactions. And of course, the material in the normal stage, it's in the rightmost of this A figure, is dominated by Heisenberg interactions in blue, But the same study also showed that the Heisenberg interactions are tunable by compressive strain, whereas the Kitaev interaction remains constant. So you can tune your material, at least in principle, to a regime in which Kitaev interactions dominate over Heisenberg ones by a modest amount of compressive strain, leading the material to a regime that is modeled by a Kitaev model with spin 3/2 plus a single ion isotropy out of plane that explains the direction of the magnetization of the unstrained compound. What is known theoretically about the spin-S Kitaev models is that they are not exactly solvable, but still displays an extensive number of conserved quantities. This time, it's not a product of the spins, but a product of exponentials of spins. And in the large S limit, you can map you can find an effective theory for your Kitaev model that's given by a toric code defined over these Kekulé patterns in figure B here. The validity of this effective toric code theory depends on this energy scale that's in purple, which corresponds to the energy, an energy scale for freezing this Kekulé pattern. And while the instability of this theory depends on the energy scale in blue here, which corresponds to the possibility of rearrangements of dimers in a single package. So it turns out that for S equals 3/2 specifically, you have that the two energy scales are the same, so nobody knew what was the ground stage of the Kitaev model specifically for this value of spin. And we had some contact with Hai-Yong Ki's group in Toronto, who tried to do DMRG simulations of the model and said that they could not identify the ground stage because they found too many low energy excitations with this method. So this model turns out to be interesting from both experimental and theoretical points of view. And we tried to solve, what was our approach to this problem was to use these operators here, the pseudo-spins and pseudo-orbital operators that we studied a lot in the context of J equals 3/2 Mach insulators. The algebra of these operators is very simple, and it turns out that there is an immediate Majorana-Fermi representation for these operators as well, and the inverse transformation from spin to these spin orbital operators. So first advantage is if you go back to the conservative operators in terms that was in that paper I showed before, they are rewritten exactly like the spin 1/2 Kitaev in model. Other advantage, we can introduce a different single ion isotropy in relation to the one I showed before. That's just proportional to this TZ pseudo-orbital. And when you insert this as a perturbation to your Kitaev model and lead this DZ parameter to the infinite limit, effectively what you're doing is to project your real spin into the pseudo-spins. So what you're doing effectively in this limit, your spin 3/2 Kitaev model behaves as the spin 1/2 Kitaev model for these pseudo-spin variables. So we have a control parameter when we are going to do the phase diagram that we did before. Okay, it's very useful to split your Kitaev model into 3 parts for analysis and understanding one important point. For the first part is the Kitaev honeycomb model for spin 1/2, just with orbital degeneracy. well, the method of integration is exactly the same, but now this theta 0 is not exactly a Majorana fermion, but a product of 3 Majorana fermions. But since this Majorana, since this Majorana fermion still obeys the algebra for the Majorana fermions, it's still integrable. You will know how to deal with this exactly. This integrable Kugel-Komsky model, that's a model with spin orbital interactions, is even simpler. We just plug into the SL6 Majorana representation I showed before directly, and you will get exactly the same gauge, Z2 gauge variable, and a free fermion problem. So, good, you know how to solve this. Now, this part here shows what's the issue, which is when you have a model that mixes both this theta 0 and the theta x, y, z operators, you have to, you find out that there is this strange same-site commutation between theta 0 and theta x, y, z. So that is what makes the model not a free fermion model, but something that is parafermionic-like. So that is what forces us into approximation, and that's what makes, this model not exactly solvable. So what we do is, we do a mean field decoupling of this part, we do a mean field decoupling of this part, make the most general mean field decoupling, find as many self-consistent solutions as we can, and take only the one with the least energy. Yeah, the U variables are all the same, and they are all the same as the Kitaev with spin 1/2.
It's the eta variable, the eta on my left.
Yes.
Okay, thank you.
Exactly. So, so that's what I was talking about. And for the isotropic case in particular, it's, we can gain a lot of insight by first solving that isotropic Kugel-Komsky model at first place, which displays 2 flat bands and 1 intermediate band with dispersion that's exactly like the spin 1/2 Kitaev model. Now, when we do the mean field approximation, turns out that all of these quadrupolar order parameters are 0, and this delta have some small values of order 0.1, which leads to small corrections, the small dispersion of the flat bands. In particular, it explains the low energy excitations that was observed by the Toronto's group, because we now see that there's almost 0 energy excitations on this theta y flat band. This point turns out to be very important because it's a point of discontinuous, marks discontinuous quantum phase transitions, as can be seen by, for example, just slightly varying the value of JZ, of the JZ coupling constant and keeping everything constant. We see that the value of the QXY order parameter goes from 0 to something large by just a small variation of each. On the left-hand side, you have a gapless quantum spin liquid that can be adiabatically connected to the gapless S = 1/2 Kitaev spin liquid. And on the right-hand side, we have a gapped quantum spin liquid, which is S = 3/2 and it cannot be adiabatically connected to the gapped S = 1/2 phase. Well, is this a problem of our mean field approximation? We don't think so, because there is an excellent quantitative agreement with DMRG for all values. So, and we have actually an explanation of it by extending a theorem for exactly solvable models to S = 3/2. And we have an interpretation that the mean field theory, Well, it's giving the best later. Oh. Sorry. Yeah. Sorry. Okay. Okay. So sorry. The mean field theory is a method to get the best single Slater determinant approximation to the real ground state of the S equal 3/2 Kitaev model. So yeah, I plan to skip this. And my main message is that we uncovered the phase diagram of the spin 3/2 Kitaev model and by extending several results of the spin 1/2 Kitaev model, and this gives opportunity to several research lines. Acknowledgements to the Munich group, special thanks to Hui Keijing, who did the DMRG calculations, and Johannes Knoll, who has been my supervisor throughout my postdocs. And being here in São Paulo, I have to acknowledge also Rodrigo and Eric for related works on J equal 3/2 Mott insulators. So many thanks.
Well, thank you, William. Questions?
Oh, sorry. Hi, very nice talk. I saw that you mentioned something in the conclusions about looking for how the gauge field acts on this ground state, right? I mean, we know that in Kitaev with spin 1/2, we have Majorana fermions, but also we have these gauge configurations, which means you fix the gauge field to determine what ground state you are, right?
Yeah.
I'm sorry. So, I was wondering, do you perform any kind of calculation like perturbation theory or something on the gauge field?
Well, if there is some kind of perturbation theory that considers fluctuations on the gauge.
Yeah, I mean, you have a mean field approximation, so
well, there
maybe
are some. I mean, Johannes has done a mean field, what he called augmented mean field theory that allows you to insert a flux perturbation. That's what allows you to estimate dynamic correlations within Parton mean field theory. There's also a recent work from Christian Batista, who developed a way to make a variational study of the Kitaev-Heisenberg gamma model using states that include 2 fluxes and 4 fluxes. So there are some studies on these lines. Yes, it's possible. But we didn't do this in this work.
Okay. I mean, I don't know if you are aware about this. One more question, right? If I can. Okay, so one more. I have one comment about that. I mean, there is a recent paper that shows some kind of duality between Rydberg Hamiltonians with quantum spin liquids. That basically means that you have some Dirac spin liquid with also a Z2 gauge field.
Okay.
And then it seems to me that these Majorana fermions are very similar to Dirac fermions in the sense that the dispersion on is gapless, right? So,
well, yeah, I'm not aware of this paper. Is it Vishwanath's paper or no? Or?
It's from Kevin Slager, Jason Alishan.
Okay, I don't know. Sorry, I don't
okay,
think I
maybe
can comment
we can
about
talk
it,
about this later, right?
Yes, sure.
Thank you. Very nice talk.
So why does Leib's theorem does not work here?
Sorry?
So Leib's theorem, why does it not apply?
Oh, Leib's theorem, yeah, sure. That's actually why we wanted to do a DMRG calculation, because DMRG is, is unbiased in the sense that we are not applying a fixed flux by onset. And in the DMRG has confirmed that the zero flux was found for all of these phases.
And what are the requirements that it applies? Like
Sorry?
under what? Why doesn't it apply here? Like, why isn't it like the theorem? Why is it not like for the 1/2 model where it's?
Well, I don't know. I don't know if I.
Why doesn't the Lieb theorem apply to your case? Why does it?
Oh,
not-
okay. Why does it apply?
Does it not apply?
Why does it not apply? Well, if we go to this case here, it applies to this model. That's exactly solvable. But this model here, this term, there are 4 fermions. And this term are 6 fermions. So Lieb's theorem is a theorem that's valid for quadratic Hamiltonians, not for quartic or sextage Hamiltonians. So that's why we know that we have the expectation that on the mean field level, it will be valid. But the question is, are we dropping things out in our mean field approximation? And that must be confirmed with DMRG.
Okay, thank you.
Hi, Willian. Thanks for the really nice talk. I was wondering about this gapped phase that you find for spin 3 halves, which is not connected to the spin 1/2 phase.
Yes.
Does it have some kind of topological order, which is the Natori code-like?
Yeah, it's a toric code-like. The difference from the... We have an idea about what's the difference between the AZ and B phases. If you remember, the toric code for Kitaev is defined on these kind of square lattices here, right? And in the case of the spin 1/2 Kitaev model, this toric code like is derived on fourth order perturbation theory. In the case of the B phase, it's derived on the 12th order perturbation theory. So yeah, we get something that's similar to this toric code in some sense, but with much lower flux excitations. So I think it has these, the same topological features of AZ, but a bit more fragile.
Okay, I see. Thanks.
Thank you, William. Thank you, everybody. Let's. Oh, I didn't see. Sorry.
Hi, William. What happened when you apply a magnetic field, for example?
Okay.
Does it have a finite
We
Ker
didn't
number?
try to do this. My guess can be based on these slides that you didn't show, which is that a magnetic field will induce something much more like this, that breaks the integrability because it will include some flux. So we can do, I think we can still do a third order perturbation theory, a la Kitaev, and then do a mean field decoupling that will induce some kind of chiral spin liquid. We didn't do this, but maybe it's something to do later. Okay?
Okay. Am I missing a last question here? Or no? Okay, so I think not. Well, thank you. So let's thank William and all the students again. And we get back here in half an hour. 11:15 here then.
Okay. Muito bom.